Hey everyone, welcome to The Explainer. So glad you're here with us today because, wow, do we have an exciting one. We're going to completely demystify the modern semiconductor industry. You hear about microchips constantly, right? But how do they actually go from a theoretical concept to becoming the beating heart of a supercomputer? We're going to break that incredible journey down step by step to make it crystal clear and honestly truly fascinating. Look, we all know the generative AI boom is demanding just unprecedented, absolute, mind-boggling amounts of compute power right now. Our driving question today is simple. How do we actually build the engines of this AI revolution? How are these cutting-edge chips realized in the physical world? Okay, let's dive into this. Here's our roadmap. 1. Designing the foundation. 2. The manufacturing miracle. 3. Architecting the AI era. And 4. The next generation. We're taking the full trip today, from open source software toolkits all the way down to extreme lithography and up through advanced packaging. Let's get to it. All right, kicking things off with section 1, designing the foundation. Because, long before a single atom of silicon is ever moved or altered in a fab, those foundational blueprints have to be meticulously coded. And that brings us straight to the PDK. A process design kit is basically a set of files and models the industry uses to map a design to a specific fabrication process. But what I really want to highlight for you is the OpenRD PDK-28. Created by the Rios Lab, it's this revolutionary open-source template custom-built for the 28-nanometer process. Now let's talk about a critical methodology called DTCO, or Design Technology Co-Optimization. The big takeaway here is that DTCO totally bridges the gap between design and manufacturing. You don't just design a chip and, toss it over the wall to the fab anymore. No way. With DTCO, design and process tech are optimized together. The result? Massively improved performance, better power efficiency, and way lower costs. And honestly, this is exactly where projects like OpenRPDK-28 become absolute game changers. It completely democratizes access by offering these proven open-source building blocks so innovators don't have to start from scratch. Why does that matter to you? Because by providing these tools, it drastically lowers the barrier to entry. It ensures a much shorter time to market and radically lower development costs for anyone out there trying to build custom silicon. Moving right along to section 2, the manufacturing miracle. Because once we've got that optimized design, pulling it from software into physical silicon takes an environment that, frankly, defies belief. It is an absolute manufacturing miracle. So, how does the physical printing actually happen? Well, ASML's extreme ultraviolet or EUV lithography prints microchips using light with a wavelength of just 13.5 nanometers. Just think about the impossible scale of that for a second. We're trying to pack billions of transistors onto a single chip. To pull that off, we have to use light that is unimaginably small, literally bordering on the X-ray range, and thousands of times thinner than a single human hair. But how do you even generate 13.5 nanometer light? Honestly, it reads like pure science fiction. Step 1, a massive CO2 laser fires. Step 2, it hits this microscopic, super fast-moving drop of molten tin. Step 3, it instantly vaporizes that tin into a high-energy plasma. And step 4, that exact plasma emits the EUV light, which gets carefully guided by a series of incredibly precise mirrors. Now, what's really interesting about this slide is the sheer mind-bending speed of this physics experiment. 50,000. That is how many times the laser fires at those microscopic tin drops every single second. Yes, you heard that right. 50,000 times a second, continuously, just to generate enough extreme light to print your chips. It's wild. But of course, there's a major catch. Because this EUV light is so extreme, it gets absorbed by absolutely everything, including the very air we breathe. Because of that, the entire light path inside the machine has to operate in a high vacuum. This fragile, carefully controlled environment is strictly necessary. Any atmospheric interference whatsoever, and it would completely ruin the delicate 4 times reduction of the pattern that's being printed onto the wafer. Which brings us to section 3, architecting the AI era. Okay, so we've designed the foundation and we've printed the wafers. Now we're going to explore how companies like AMD take these printed pieces of silicon and architect them into the massive GPUs that power today's data centers. And this brilliantly illustrates the exact shift we're seeing in chip design. Look at AMD's CDNA4 architecture. They've completely moved away from the old-school method of building one giant monolithic chip. Instead, they're taking these specialized, smaller chips, we call them chiplets, and stacking them both vertically and horizontally onto a single unified package.
The real genius of this chiplet strategy becomes perfectly clear when we look at the manufacturing nodes. AMD is actually mixing different process nodes right there on the exact same package. For instance, they use the absolute cutting-edge TSMC N3P node for the XCD compute chiplets, because that's where you need the raw performance. But then, they pair it with a highly efficient TSMC N6 node for the IOD infrastructure dies. This kind of heterogeneous integration is huge. It lets them optimize for maximum AI throughput and manufacturing efficiency at the exact same time.
To really grasp the massive scale required for modern generative AI and scientific workloads, just take a look at the specs for the AMD Instinct MI355X. First off, it draws 1,400 watts. To put that into perspective, that's basically like running a high-end microwave on full blast continuously inside a server rack. Naturally, you need direct liquid cooling for that. On top of that, it packs an unbelievable 288 gigabytes of HBM3E memory. It pushes an astonishing 8 terabytes per second of memory bandwidth and over 1 terabyte per second of communication bandwidth. It is literally an absolute powerhouse. But hey, reaching these incredible speeds isn't just about brute force hardware, right? It's also about much smarter math. 3.85x. That is the staggering performance boost this architecture achieves over the previous generation's FP8 format. How do they do it? By supporting new reduced precision numerical formats like MXFP4 and MXFP6. Basically, by shrinking the data types, they squeeze dramatically more computational throughput out of the exact same physical silicon. It's this incredibly elegant software optimization that just unlocks massive hardware gains. All right, let's step into our final section, Section 4, the next generation. Because the semiconductor race absolutely never stops. While we're sitting here just trying to wrap our heads around today's hardware, the industry is already deep into prepping for the late 2020s. When we plot all of this out, a pretty clear chronological roadmap for the future emerges. In 2025 and 2026, ASML's next-generation high-NA EUV systems will start supporting high-volume manufacturing, and that directly links into 2027, when TSMC's Taichung fab is expected to begin trial production, which, in turn, paves the way for 2028, when AMD's Zen 7 architecture is expected to hit mass production. It's like a giant puzzle. One breakthrough literally sets the stage for the next. Now, looking at what the supply chain is reporting for that 2028 window, we're seeing some totally fascinating industry rumors surrounding AMD's Zen 7 Grimlock architecture. Sources are pointing to the use of the insanely dense TSMC 1.4 nanometer, or A14 node. For assembly, there are reports of them evaluating FOPLP, which stands for Fan-Out Panel-Level Packaging, from vendors like PowerTech. We're also seeing expectations of up to 16 cores per compute die, and of course the continued integration of AI compute extensions, or ACE. Now, obviously these are just reports, but they clearly illustrate exactly where the industry is aiming next. Which leaves us with this final, deeply provocative question. As we approach 1.4 nanometers, how much smaller can silicon truly go? We are literally pushing the absolute extreme boundaries of Moore's law, and honestly, physics itself, just to keep this AI revolution spinning. Thank you so much for joining me on this explainer today. I really hope this deep dive helped illuminate the incredible pipeline of silicon creation for you. Keep questioning, keep learning, and I'll catch you next time.